Welcome to Fiber Community Manual Practical 2. Request like, subscribe, press bell icon, share and comment. This is a sample of certificate index. We already discussed practical 1. Now in this video lecture we will discuss practical 2, that is about to write Scilab code for given example of transmission characteristic of optical fibers. Practical 2 is about transmission characteristic of optical fibers. Aim is to write Scilab code for the given example of transmission characteristic optical fiber. Software is Scilab version 6.1.0. First, attenuation. Attenuation or transmission loss of optical fiber has proved to be one of the most important factors in bringing about the wide acceptance in telecommunication. Attenuation is power loss taking place inside the fiber optic cable. Because of this loss, the amplitude of signal passing through fiber optic cables get reduced. Signal attenuation is usually expressed in the logarithmic unit of the decibel. The decibel may be defined for a particular optical wavelength as the ratio of input transmitted optical power into a fiber to the output received optical fiber from the, as given equation 2.1. Number of decibel, that is equal to 10 log 10 pi by pu. So we can write pi by pu, that is equal to 10 raised to tb divided by 10, equation 2.2. In optical fiber communication, the attenuation is usually expressed in decibel per unit length. Following equation 2.3, alpha dB into L, that is equal to 10 log 10 pi by pu, where alpha suffix dB is the signal attenuation per unit length in decibel, which is also referred to as the fiber loss parameter, and L is the fiber length. P suffix I is the input power of the cable and P suffix O is the output power of the cable. Absorption. Material absorption is a loss mechanism related to the material composition and the fabrication process for the fiber, which result in the dissipation of some of the transmitted optical power as a heat in the waveguide. The factors contributing to material absorption loss are as follows: intrinsic absorption due to basic atoms of the fiber material, extrinsic absorption due to impurity atoms, absorption due to atomic defect in the glass material. And intrinsic absorption. Pure silica based glass has two major intrinsic absorption mechanisms at optical wavelength. First, a fundamental UV absorption edge. The peaks are centered in the ultraviolet wavelength region. This is due to the electron transition within the glass molecules. The tail of this peak may extend into the shorter wavelength of the fiber transmission spectral window. Second, the fundamental infrared and far infrared absorption edge. Due to molecular vibrations such as SiO, the TL of this absorption peak may extend into the longer wavelength of the fiber transmission spectral window. Extrinsic absorption. Major extrinsic loss mechanism is caused by absorption due to water as a hydroxyl or OH ions introduced in the glass fiber during fiber pooling by means of oxyhydrogen flame. These OH ions are bonded into the glass structure and have absorption peaks due to molecular vibration at 1.38 mm. Since these OH absorption peaks are sharply peaked, narrow spectral windows exist around 1.3 mm and 1.5 mm, which are essentially unaffected by OH absorption. The lowest attenuation for typical silica-based fiber occur at wavelength 1.55 mm at about 0.2 dB per kilometer, approaching the minimum possible attenuation at this wavelength. Third is scattering loss. The loss of the signal caused by diffusion of the light beam is known as a scattering loss. The diffusion itself is caused by microscopic variation in the transmission medium. The major factors affecting the scattering loss are as follows. First is a variation in the density of material. Second, composition fluctuation. And third, defects present in the optical fiber. Figure 2.1 represents a classification of scattering. Scattering, linear and nonlinear. In linear, Rayleigh scattering, mass scattering. In nonlinear, stimulated Boolean scattering and Raman scattering. The Rayleigh scattering laws is inversely proportional to the fourth order of the wavelength. The Rayleigh scattering formula for a single component glass given by equation 2.4, that is gamma r, that is equal to 8 pi cube n raised to 8 p square beta c ktf divided by 3 lambda 4, where gamma is the Rayleigh scattering coefficient, lambda is the optical wavelength, n is the refractive index of the medium, p is the average photoelastic coefficient, beta suffix c is the isothermal compressibility at the fictive temperature T suffix f, and k is the Boltzmann constant. The Rayleigh scattering coefficient is related to the transmission loss factor or transmissivity of the fiber following the relation by given 2.5. So transmittivity equal to exponential minus gamma r into L, where L is the length of the fiber. Brilliant scattering is only a significant above threshold power density, assuming that the polarization state of the transmitted light is not maintained. It may be shown that threshold power Pb is given by Pb is equal to 4.4 10 raised to minus 3 d square lambda square alpha dB into V watts, that is 2.6, where d and lambda are the fiber core diameter and the operating wavelength respectively, both measured in micrometer. Alpha dB is the fiber attenuation decibel per kilometer and V is the source bandwidth for injection laser in gigahertz. The stimulated Raman scattering is similar to stimulated Boolean scattering, except that a high frequency optical phonon rather than acoustic phonon is generated in the scattering process. Also, SRS skin occurs in both the forward and backward direction in an optical fiber and may have an optical power threshold of up to 3 order of magnitude higher than the Boolean threshold in a particular fiber. The threshold optical power for SRS in a long single mogul fiber is given by PR is equal to P 5.9 into 10 raised to minus 2 d square lambda alpha dB watts, where d, lambda and alpha dB are specified as 2.6. Fourth is a fiber band loss. Optical fibers suffer a radiation loss at bands or curves on their path. This is due to the energy in the evanescent field at the band exceeding the velocity of light in the cladding, and hence the guidance mechanism is inhibited, which cause light energy to be radiated from the fiber. The loss can generally be represented by the radiation attenuation coefficient, which is given as equation 2.8 alpha suffix r, that is equal to C1 exponential of minus C2r, where r is the radius of curvature of the fiber band and C1 and C2 are constant which are independent of r. Furthermore, large bending loss tend to occur in the multimode fiber at a critical radius curvature r suffix c, which may be estimated from r suffix c is equal to 3 n1 square lambda divided by 4 pi n1 square minus n2 square 3 by 2, equation 2.9, where n1 is the refractive index of the core and n2 is the refractive index of the cladding. It may be observed from the expression given in equation 2.9 that the potential macrobending loss may be reduced by a designing a fiber with a large relative refractive index difference operating at the shortest wavelength possible. The critical radius of the curvature for a single mode of fiber can be estimated at equation 2.10, that is equal to r is equal to 20 lambda divided by n1 minus n2 raised to 3 by 2 into 2.748 minus 0.996 lambda by lambda c raised to minus 3, where lambda c is the cutoff wavelength for single mode of fiber. Then fifth is a dispersion. Dispersion of the transmitted optical signal causes distortion for both digital and analog transmission along optical fiber. For no overlapping of light pulse down on an optical fiber link, the digital bitrate beta suffix t, b suffix t must be less than the reciprocal of the broaden through dispersion pulse duration tau, to tau. This is given as equation 2.11 b suffix t, that is less than or equal to 1 upon 2 tau. The maximum bit rate is given approximately by b suffix t maximum, that is less than or equal to 0.2 divided by sigma bit second inverse. Equation 2.12. Dispersion are of three types: intermodal dispersion or modal delay, polarization mode dispersion PMD, and intramodular dispersion. In that, material dispersion and waveguide dispersion. RMS pulse broadening due to material dispersion is given by equation 2.13, that is sigma suffix f equal to sigma lambda L into C in multiplication of lambda d square of n1 divided by d lambda square. However, material dispersion parameter capital M defined as equation 2.14, M is equal to dTm divided by d lambda into L, that is equal to lambda by C into d square n1 by d lambda square, which is often expressed in units of PS, nanometer inverse, kilometer inverse. Therefore, RMS pulse broadening in terms of material dispersion parameter M, sigma M is equal to sigma lambda L into M divided by 2.15. The delay difference between the extreme meridional ray and the axial ray is given by as delta Ts, that is equal to T max minus T min, that is equal to L ns square divided by 2n1c, equation 2.17. The RMS pulse broadening due to internal dispersion or standard deviation is given as sigma sub x, that is L n1 delta divided by 2 into 3 1 by 2 c, or equal to L into n1 square 4 by 3 raised to 1 by 2 n1c, equation 2.17. So these all the equations are used while we discuss in the example. So let's move to the example. Question 1. The radiative and non-radiative recomposition lifetime of a minority carrier in the active region of a double heterojunction LED are 60 nanosecond and 100 nanosecond respectively. Determine the total carrier recomposition lifetime and the power internally generated within the device when the peak emission wavelength is 0.87 micrometer at a drive current of 14 milliamp. When the mean of power launched into an 8 km length of fiber is 120 microwatt, the mean optical power at the fiber output is 3 microwatt. To determine, first, the overall signal attenuation or loss in decibel through the fiber, assuming there are no connector or splice. Second, the signal attenuation per kilometer for the fiber. The overall signal attenuation for a 10 km optical link using the same fiber with a splice at a 1 km interval, each giving an attenuation of 1 dB. And fourth, the numerical input-output power ratio in C. So, and given data 1, that length of fiber, optical power, Pi, PO, and we have to find the signal attenuation per kilometer, overall signal attenuation for 10 km optical link with the splice at 1 km interval, and finally Pi by Pi ratio. So for this example, we have to use equation 2.1, 2.2, and 2.3. Pi is 120 microwatt input optical power, PO is equal to 3 microwatt output optical power, L is equal to 8 kilometer fiber length, alpha dB, L that is equal to 10 log 10 Pi by PO. This is the first option, overall signal attenuation. Alpha suffix d, that is equal to alpha dB L divided by L, signal attenuation per kilometer, second option. A is equal to alpha dB into 10 plus 9, overall signal attenuation for 10 km optical length with splices. Okay, so in this case 10 km optical length with splice at 1 km. So that's why plus 9 is there. So this is a good example. Then Pi by PO, that is equal to 10 raised to round of a divided by 10. So there is a numerical input-output power ratio. And finally, display the result. So printf overall signal attenuation, printf signal attenuation per kilometer, printf overall signal attenuation for 10 km optical link with splice, and printf numerical input-output power ratio. So let's do this example in the Scilab. Okay, so this is given alpha dB. Then we use equation 2.1, 2.2, and 2.3 to solve this example, and finally displaying the result. So code as it is. Now execute this code in the Scilab. Execute, and this is the result. So overall signal attenuation is 16 dB. Signal attenuation per kilometer is 2 dB per kilometer. Overall signal attenuation for 10 km optical link with splice is 29 dB. And numerical input-output power ratio is 794.3. Next, question 2. Silica has estimate fictive temperature of 400 K with an isothermal compressibility of 7 into 10 raised to minus 11 meters square into inverse. The refractive index and the photoelastic coefficient for silica are 1.46 and 0.286 respectively. Determine theoretical attenuation in decibel per kilometer due to fundamental wave scattering in silica at optical wavelength of 0.631 and 1.3 micrometer. Boltzmann constant is 1.381 10 to minus 21 joule per K. As per given in data 2, and P, beta C, K, TF, and L is given. Find gamma R and L at different wavelengths. Use equation 2.4 and 2.5 to solve this example. N is equal to 1.46 refractive index, P is equal to 0.286 photoelastic coefficient, beta suffix C equal to 7 into 10 to 11, that is the isothermal compressibility. K is equal to 1.381 into 10 to minus 23, that is the Boltzmann constant. T suffix F equal to 1400, that is a Kelvin, that is a fictive temperature. L is equal to 1000 meter, that is a fiber wavelength. First option. So attenuation in dB per kilometer due to fundamental wave scattering at 0.63 micrometer. So lambda is equal to 0.63 10 to minus 6, that is in meter wavelength. Then use equation gamma R is equal to 8 pi cube and raised to 8 p square into beta c KTF divided by 3 lambda raised to 4. And for L at kilometer, exponential of minus gamma R into L. And in A1 that is equal to 10 log 10 1 upon L in kilometer. Now same procedure, but same formula for gamma R, L, Km and A, but for different wavelength. So attenuation in dB per kilometer due to the fundamental wave scattering at 1 micrometer. Lambda is equal to 1 into 10 raised to minus 6 meter wavelength. Gamma R is equal to 8 pi raised to cube n square p raised n raised to 8 p square beta c KTF divided by 3 lambda 4. L kilometer 2, that is exponential minus gamma R into L, and A2 is equal to 10 to 10 log 10 1 upon L by kilometer, L kilometer. Now third same, just differentiate the operating, just the value of operating wavelength is different. So attenuation dB per kilometer due to fundamental wave scattering at 1.30 micrometer. Lambda is equal to 1.30 into 10 raised to minus 6 meter wavelength. Gamma R equal to 8 pi cube n raised to 8 p square beta c KTF divided by 3 over 4. L in kilometer is exponential of minus gamma RL. A3 is equal to 10 log 10 1 upon L kilometer. And finally displaying the result for 3 optical wavelengths. So printf attenuation in dB per kilometer due to fundamental wave scattering at 0.63 micrometer. Printf attenuation in dB per kilometer due to fundamental wave scattering at 1 micrometer. And printf attenuation in dB per kilometer due to fundamental wave scattering at 1.30 micrometer. Let's try to run this program in the Scilab and check the result. So code is same that we discussed. Just we have to execute this program in the Scilab and check the result. 7 execute. Okay, so attenuation in dB per kilometer due to fundamental scattering at 0.63 micrometer is 5.2 dB per kilometer. Attenuation dB per kilometer due to fundamental scattering at 1 micrometer is equal to 0.8 dB per kilometer. And attenuation in dB per kilometer due to fundamental scattering at 1.30 micrometer is 0.3 dB per kilometer. So you can see the when operating wavelength is changed, accordingly its relative scattering value is changed. So we already discussed this in the equation. That is gamma R is inversely proportional to lambda raised to 4. Then next example, that a long single mode optical fiber has an attenuation of 0.5 dB per kilometer when operating at a wavelength of 1.3 micrometer. The fiber core diameter is 6 micrometer and the laser source bandwidth is 600 megahertz. Compare the threshold optical power for stimulated Boolean and Raman scattering within the fiber at a wavelength specified. So in this given data, d, lambda, alpha dB, v, and find p suffix b and p suffix r. So use equation 2.6 and 2.7 that is discussed in this module. Alpha dB is equal to 0.5 dB per kilometer attenuation. Lambda is equal to 1.3 micrometer operating wavelength. D is equal to 6 micrometer fiber core diameter. And U is equal to 0.6, it is the gigahertz laser source bandwidth. So use formula 2.46, that is the P is equal to 4.4 10 raised to minus 3 d square lambda square into alpha dB. Nu, that is a threshold optical power for SDS, And PR is equal to 5.9 10 raised to minus 2 d square lambda alpha dB. That is a threshold optical power for SRS. And displaying the result. So printf the threshold optical power for SBS and threshold optical power for SRS. Just run this program in the Scilab. So code is same, execute. So the threshold optical power for SBS is 80.3 milliwatt and the threshold optical power for SRS is 1.38 watt. Example 4, the two-step index fiber exhibit the following parameters. A multimode fiber with a co-refractive index of 1.5, a relative refractive index difference of 3% and an operating wavelength of 0.82 micrometer. B, an 8 micrometer core diameter single mode fiber with a co-refractive index the same as a relative refractive index difference of 0.3% and an operating wavelength of 1.55 micrometer. Estimate the critical radius of curvature at which large bending loss occur in both the case. So as per given data, N1 delta wavelength is given. Use equation 2.9 and 2.2 to solve this example. N1 is equal to 1.5 meter length, delta is equal to 0.03, 100% relative refractive index difference. Lambda is equal to 0.82 10 raised to minus 6 meter operating wavelength. So calculation of radius of curvature of multimode fiber with the help of equation 2.9. That n square, okay, so first n square is n2 is equal to square n square minus 2 delta n1 square and RC is equal to 3 n square lambda divided by 4 pi n1 square minus n2 square raised to 3 by 2. Now for calculating option B, I use equation 2.10. Okay, so n1 is 1.5, delta is 0.03, relative refractive index difference lambda is equal to 1.55 10 raised to minus 6 meter. Operating wavelength D is equal to 8 10 raised to minus 6 meter core diameter. Calculation of the radius of curvature of a single mode fiber. So n2 is equal to square 2 n1 square minus 2 delta n1 square. A is equal to d by 2 lambda c is equal to 2 pi a n1 square root 2 delta divided by 2.405 and RCS. So 20 lambda in bracket 2.748 minus 0.996 lambda by lambda c raised to minus 3 and divided by n1 minus n2 raised to 3 by 2. Finally, display the result. So printf the radius of curvature of multimode fiber and printf the radius of curvature for a single mode fiber. Okay, let's try to run this program in the Scilab and check the result. So code as we have explained already, just we run this program in the Scilab. So execute, save and execute. So the radius of curvature of multimode fiber is 9 micrometer and the radius of curvature for single mode fiber is 32 millimeter. Next example, a multimode gradient index fiber exhibits a total pulse broadening of 0.1 microsecond over a distance of 15 km. Estimate the maximum possible bandwidth on the link assuming no interference, the pulse dispersion per unit length, and C the bandwidth length product for fiber. So use the given data as per 5, use equation 2.11. So tau is equal to 0.1 10 raised to minus 6 second total pulse broadening. L is equal to 15 kilometer distance. B in optical there is a 1 by 2 tau. Option A, that is the maximum possible bandwidth on the link assuming no interference. Dispersion, that is equal to tau by L, the pulse dispersion per unit length. And B optical into L, that is equal to B optical into L, that is a bandwidth length product of the fiber. And so display the result. Printf the maximum possible bandwidth on the link assuming no intersymbol interference. Printf the pulse dispersion per unit length. Printf the bandwidth length product for the fiber. So let's run this program in the Scilab to check the result. Okay, so the maximum possible bandwidth on the link assuming no intersymbol interference is 5 MHz. The pulse dispersion per unit length is 6.67 nanosecond per kilometer. The bandwidth length product for the fiber is 75 megahertz kilometer. Okay. Next example. Question 6. A glass fiber exhibits a material dispersion given by in mode lambda square d square n1 d lambda square of 0.025. Determine the material dispersion parameter at a wavelength of 0.85 micrometer and estimate the RMS pulse broadening per kilometer for a good LED source with an RMS spectral width of 20 nanometer at this wavelength. So use as per given data in 6 and use equation 2.13, 2.14 and 2.15 to solve this example. Lambda is equal to 0.85 10 raised to minus 6 meter wavelength, L is equal to 1 kilometer distance, M suffix D is equal to 0.025 material dispersion, C is equal to 2.998 into 10 raised to 8 meter per second velocity of light in vacuum, sigma suffix lambda that is equal to 20 into 10 raised to minus 9 meter RMS spectral width, M is equal to MD divided by lambda C material dispersion parameter, and sigma suffix M is equal to sigma suffix lambda into L into M RMS pulse broadening per kilometer. And finally displaying the result. Printf the material dispersion parameter is and printf pulse broadening per kilometer is. Let's run this program in the Scilab. Execute. Program is same. Just to run this program. See result in the console window. So material dispersion parameter is 98.1 picosecond per nanometer per kilometer, and RMS pulse broadening per kilometer is 1.96 nanosecond per kilometer. Next example. Estimate the RMS pulse broadening per kilometer for the fiber in example 6 when the optical source used in the injection laser with a relative spectral width sigma lambda by lambda of 0.0012 at a wavelength of 0.85 micrometer. So as per given data 7, use equation 2.15 to solve this example. Lambda is equal to 0.85 10 raised to minus 6 meter wavelength, L equal to 1 kilometer distance, M suffix D is 0.025 material dispersion, C is equal to 2.998 10 raised to minus 8 meter per second velocity of light in vacuum, sigma lambda by lambda that is equal to 0.0012, M equal to M suffix D divided by lambda C material dispersion parameter, sigma lambda is equal to sigma lambda by lambda into lambda, so RMS spectral width, and sigma M that is sigma lambda into L into M RMS pulse broadening per kilometer. And finally display the result. Printf RMS pulse broadening per kilometer. So let's run this program in the Scilab. So program as it is what we discussed, we have just checked if any kind of error or not. So execute this program, save and execute. Okay, so RMS pulse broadening per kilometer is 0.10 nanosecond per kilometer. Okay. The next example. A 6 kilometer optical link consists of multimode step in this fiber with a co-refractive index of 1.5 and a relative refractive index difference of 1%. Estimate the delay difference between the slowest and fastest mode at the fiber output, the RMS pulse broadening due to intermodal dispersion on the link, the maximum bit rate that may be obtained without sustained errors on the link assuming only intermodal dispersion, and the bandwidth length product corresponding to option C. So use the given data and the equation 2.12, 2.16 and 2.17 to solve this example. Delta is equal to 0.01 100% relative refractive index difference, then L is equal to 6 kilometer length of the optical wing, N1 is equal to 1.5 co-refractive index, C is equal to 2.998 into 10 raised to 8 meter per second velocity of light in vacuum. So first calculate the option A, the delay difference between the slowest and fastest mode at the fiber output. So delta TS that is equal to L into N1 into delta divided by C. Option B, the RMS pulse broadening due to intermodal dispersion on the link. So sigma S that is equal to L into N1 into delta divided by 2 square root 3 into C. Option C, the maximum bit rate that is bit 60 equal to 1 upon 2 delta TS. Improve maximum bit rate is equal to B suffix Ti equal to 0.2 divided by sigma s. And B optical into L, that is equal to BTI into L, that is given option D, that is bandwidth length product corresponding to option C. And finally, displaying the result. Printf, the delay difference between the slowest and fastest mode at the fiber output. Printf, the RMS pulse broadening due to intermodal dispersion on the link. Printf, the maximum bit rate and improved bit rate. Printf, bandwidth length product. So let's run this program in the Scilab. So code same as we discussed. Execute this code. Save and execute. So answer is the delay difference between the slowest and fastest mode at the fiber output is 300 nanosecond. The RMS pulse broadening due to intermodal dispersion on the link is 86.7 nanosecond. The maximum bit rate is 1.7 megabit per second and improved bit rate is 2.3 megabit per second. And bandwidth length product is 13.8 megahertz kilometer. So that's it from this example. Conclusion, this experiment is about to know what is transmission characteristic of optical fiber. When light signal travels on optical fiber cable, it loses part of its strength due to different types of losses. This experiment also demonstrates mathematical equation with example of transmission characteristic of optical fiber. Note, demonstrated examples are given in Optical Fiber Communication Principle and Practice, John M. Senior book, Pearson, 3rd edition. Example number is 3.1, 3.2, 3.3, 3.4, 3.5, 3.6, 3.7, and 3.8. Thank you. Once again, request to like, subscribe, share, comment. Do not forget to press bell icon. Thank you once again.